Welcome to the class 5 of Basic Electronics. Today we are going to discuss about how to solve the problems or the circuits by using Thevenin's theorem, that is step-by-step procedure to solve Thevenin's theorem. So first you have to remember how to solve the Thevenin's theorem. First one, identify the element for which the current or voltage is to be found and consider it as a load resistor. So when the problem is given to you, this is the problem, very simple problem. Using Thevenin's theorem, determine V of naught. So this is the given problem and a circuit. So we have to solve the circuit by using Thevenin's theorem. So in the first step, you have to identify the element for which the current or a voltage is to be found and consider it as load resistor. So here what they are asking us to determine V of naught, that is through this 4 ohm resistor. So once you identify the element, that is this 4 ohms resistor, through which I have to find out V of naught. So consider this as the load resistor. Now open the load resistor and measure the voltage across the terminals. So open this and measure the load across this, say A and B. So to find the Thevenin's equivalent circuit, first break the circuit at the load, that is at the 4 ohm load. So once I remove this load resistor, I will get a circuit like this. So open the load resistor. Next one, once you remove the load resistor, replace all voltage and current sources by their internal resistance. So this is the third step. Then measure the equivalent resistance as viewed from the open circuited terminals. This is Thevenin's resistance. Next one, draw the Thevenin's equivalent circuit with Thevenin's voltage in series with Thevenin resistance followed by the load resistor. Last, to find the current through the load resistor by simply applying Ohm's law. So these are some steps where we are going to solve the Thevenin's theorem. By using the Thevenin's theorem, we are going to solve some circuits. So the first step is to identify the element for which the current or a voltage is to be found. Here the voltage is to be found throughout the 4 ohm resistor. First you have to remove this, that is to break this circuit at the 4 ohms load. So here we have to find an equivalent circuit that contains only an independent voltage source in series with a resistor as shown in the diagram, in such a way that the current voltage relationship at the load is not changed. So this one I have to remove this at the load. Then I have to draw a simple circuit where all the internal resistances are replaced by a single resistor, that is called resistance RTH. So now we need to find VTH first and RTH. VTH is equal to the open circuit voltage VOC. The current of 2 ohm resistor is 0 here because one end of the resistor is open and another one is connected. So the current of 2 ohm resistor is 0 because one of its terminals is not connected to any element. Therefore, the current cannot pass through it. Since the current of 2 ohm resistor is 0, the 9 volt voltage is between 3 ohms and 6 ohms. There is a 9 volt voltage source, 3 ohms and 6 ohm resistor form a voltage divider circuit. The voltage across 6 ohm resistor can be determined now. Now that current of 2 ohm resistor is 0, Thevenin's theorem guarantees that VTH equal to VOC. It is not saying that VOC is the voltage across the load in the original circuit. Find the current through 6 ohm resistor and then calculate the Thevenin's voltage. So calculation of voltage across 6 ohm resistor, that is across this, that is I equal to V by R. So that is by using the Ohm's law, V equal to I into R. So I is equal to V by R. There the given voltage is 9 volt. This 2, the source is connected to in between 3 and 6 ohms now. The other end is connected to the 2 ohms, which is open here. So the resistance here, this is open. So that the current of 2 ohm resistor is 0. So just consider this part. So I equal to, now I is flowing through here. I equal to V by R. That is 9 volt divided by 3 plus 6. So this becomes 1 amp. Once I find the value of I, now it is very easy to find the VTH. V equal to I into R. That is the voltage across 6 ohm resistor. That is V equal to I we have already calculated, that is 1 ampere into R, 6 ohm resistor. So this is nothing but 6 volt. So the Thevenin's voltage is 6 volt. Now we need to find RTH. An easy way to find RTH for the circuit without dependent sources is to turn off independent sources and find the equivalent resistance seen from the port. Recall that voltage source should be replaced with short circuit. So here you have to replace, that is a voltage source, with short circuit. That means you have to remove the voltage source and you have to short circuit the terminals. And current sources as the open circuit. As there is no current sources, to keep it as an open circuit, we have only one voltage source like this, which is connected in between the terminals 3 ohms and 6 ohms. So here there is only one voltage source that should be replaced by a short circuit. Now once I replace the voltage source with a short circuit, now you can see here both the terminals of a 3 ohm and 6 ohm resistor is connected to each other. So we have to consider these two as the parallel combination, which is connected to the 2 ohm resistor with this is nothing but a series connection, because one end of the connection is open. So here replace the 9 volt voltage source by a short circuit to find the equivalent resistor. In our diagram, 3 ohms and 6 ohm resistors are connected in parallel and then connected in series to the 2 ohm resistor. So the RTH now here, or you can call it as the R of equivalent resistor. 3 ohm is connected to the 6 ohms. So R1, R2 divided by R1 plus R2. R1, 3 ohms, R2, 6 ohms, R1 plus R2, 3 ohms plus 6 ohms, which is connected in series to the 2 ohms. So this becomes 4 ohm resistance. So once you find the value of a VTH and RTH, now draw the Thevenin's equivalent circuit which consists of VTH in series with RTH and which is connected to the load. Once you know the value of VTH or RTH, now draw the Thevenin's equivalent circuit for the given circuit to calculate V of naught. Draw the Thevenin's voltage in series with Thevenin's resistance and add load resistor in series with the circuit. Now here you can see the calculated VTH is 6 volt, calculated RTH is 4 ohms, and the load. A load may be a single resistor or a circuit. A load, that is 4 ohms. So I is equal to 6 volt, which is connected to the series combination of these two. So that is nothing but I equal to, again V equal to I into R, that is 6 volt divided by 4 ohms plus 4 ohms, that is equal to 0.75 amps. So V of naught now, that is voltage across the 4 volt, voltage across the 4 ohms, 0.75 amps into 4 ohms. This is nothing but 3 volt. Since 4 ohm and 4 ohm resistors are connected in series, you can simply apply Ohm's law to find the load current. In other way, apply the given formula to find the load current directly. So here it is I of L, that is the load current, is equal to V of TH, that is Thevenin's voltage, divided by Thevenin's resistance plus load current, load resistor. So this is equal to 6 volt, again 4 ohms plus 4 ohms, that is 0.75 amps. And here you can also find the power at the 4 ohms, that is P of L, that is I square into R, power equal to, that is 0.75 amps plus of 4 ohms, this is 2.25 watts. So this is how to find out the value of VTH and RTH, or to solve the circuit by using Thevenin's theorem. Now let us go for the second problem. Find the load current and the power delivered to the load. So this is the given circuit. So what is our first step to solve this? So identify what we have to find. So that is power delivered to the load. So where is the load here? The load is given at this terminal, 5 ohm. So what is the first step? To identify the element for which the current or voltage is to be found and consider it as a load resistor. Then we have to open the load resistor. Since the terminals are open circuited, no current will flow through the resistor which is connected to the load, that is 3 ohm resistor. So the Thevenin's voltage will be the voltage drop across the second one, previous resistor, which is connected in parallel to the voltage source. So the Thevenin's voltage will be the voltage drop across 8 ohms. So that is nothing but I equal to 24 volt divided by 2 plus 8 ohms. So this is nothing but 2.4 amps. So VTH equal to, that is across 8 ohms. So this is 2.4 amps into 8 ohms, that is 19.2 volt. So now what is the second step? To replace the 24 volt, that is the voltage source, by a short circuit to find the equivalent resistance. So once I remove the voltage source by a short circuit, or replacing the voltage source by the short circuit, here these two, that is R1 and R2, that is nothing but 2 ohms and 8 ohms resistor are connected in parallel, and this parallel connection is in series with a 3 ohm resistor. So RTH becomes now, that is 2 ohms into 8 ohms, 2 ohms divided by 2 ohms plus 8 ohms. That is, this combination is now connected in series to the 3 ohms. The combination of 2 and 8 ohm resistor is connected in series to this. So RTH becomes, so this is the combination of parallel combination, that is 2 ohms, 8 ohms divided by 2 ohms plus 8 ohms. plus 3 ohms, that is 4.6 ohms. Now draw the Thevenin's equivalent circuit for the given circuit once you know the value of VTH and RTH. So now draw the Thevenin's equivalent circuit for the given circuit. Draw the Thevenin's voltage in series with Thevenin's resistance and add the load resistor. So that is I of L, that is load current. VTH divided by RTH plus RFL. So this is 19.2. RTH is 4.6 ohms and RFL is nothing but our 5 ohm resistor. So this becomes 2 amps. So this is nothing but power. This is nothing but I square into R. So this is 2 amps, 2 square into 5. Load resistor 5 ohms. So this is nothing but 20 watt. So this is how one can solve the circuit by using Thevenin's theorem. Now let us go for the Norton's theorem and find out the values. So what are the steps for solving Thevenin's theorem? We already know now. Now go for the Norton's theorem. So using the Norton's theorem, find the current in 8 ohm resistor in the network shown in the diagram. So this is the circuit. If I consider this one as the two R1, R2, R3. Now in order to find the current through the load resistance IFL, the load resistance has to be short circuited. You remember this? While solving the Norton's theorem, the load resistance has to be short circuited. But as per the Thevenin's theorem, the load resistance has to be open circuit. So we have to keep it open. We have to keep it open for the Thevenin's theorem, and for the Norton's theorem, we have to short circuit it. The load resistance 8 ohms is to be removed, and the terminal AB is to short circuited. The current that flows through AB now, that is, now once I connected like this, now here what is going to happen if I short circuited this? After removing the load resistance, that is 8 ohms. Now you can see here, the 5 ohm resistor is connected to the 6 ohms parallelly. That is, these two terminals are connected in parallel and is connected in series to the R1. So here the combination is R1 is parallel to the combination of R2 plus R3. So R1 plus R2 into R3 divided by R2 plus R3. Now substitute the values here. 4 ohms plus combination of 5 ohm and 6 ohms, that is 5 ohms into 6 ohms divided by 5 ohms plus 6 ohms. This is nothing but 6.727 ohms. The value of the current I flowing in the circuit is found out by the equation. That is, again, by using the Ohm's law, V equal to I into R. So I is equal to V by R. So V is given voltage source, that is 40 volt. Then what about this combination? So this combination is nothing but 6.727 ohms. This is nothing but 5.94 amps. So once you found the value of I now go for the short circuited current. That is, a short circuited current is given by the equation, that is short circuited current equal to I of N, I into R. This is nothing but 5.94 into 6 divided by 6 plus 5, that is nothing but 3.24 amps. Now the short circuit is removed. This part, short circuit is removed. And the independent source is deactivated. That means it's again short circuited. Now the RTH is nothing but, here it is. Once I remove this, the one end of this terminal R2 is open. So these two combinations R1 and R3 becomes parallel. So this parallel combination is connected with a series combination. So this becomes R2 plus R1 R3 divided by R1 plus R3 equal to 4 ohms into 4 ohms divided by 4 ohms plus 6 ohms plus of 5 ohms. So this is the combination. So this is nothing but 7.4 ohms. Now once you know the value of RTH and IN, Norton's current, draw the Norton's equivalent circuit behind the terminals AB parallel with the resistance when load 8 ohms is connected now across the terminals. Therefore, I of L equal to the current across the load equal to I of N into Rn divided by Rn plus RL. So in the previous section, we used to find out I, that is nothing but by using IL equal to VTH divided by RTH plus RL. Here it is I of L in Norton's theorem. That is IL equal to IN into RN instead of VTH. It is Norton's resistance. This is Thevenin's voltage. So Norton's resistance plus R into L. So by substituting the values, so here I am getting 3.24 into 7.4 volt divided by 8 ohms plus 7.4 ohms. That is equal to 1.55 amperes. So once you find out the values of IL and IN, now draw an equivalent circuit. So now, what are the applications of Thevenin's and Norton's theorem here? The one of the main application of Thevenin's and Norton's theorem is the replacement of a large part of a network, often a complicated and uninteresting part, by a very simple equivalent. And the new simplest or simpler circuit enables us to make rapid calculations of the voltage or current and hence power which the original circuit is able to deliver to the load. It also helps us to choose the best value of the load resistance or impedance required to accomplish the maximum transfer of power. So there are some limitations also. There are some limitations in solving the Thevenin's and Norton's theorem. Not applicable to the circuit consisting of unilateral elements like diodes, etc. Not applicable to the circuits consisting of non-linear elements like diode, transistors, etc. Not applicable to the circuits consisting of a load series or parallel with controlled or dependent sources, and not applicable to the circuits consisting of magnetic coupling between the load and any other circuit elements. So these are some applications of Thevenin's and Norton's theorem and limitations of Thevenin's and Norton's theorem.